For decades, it has been the prevailing wisdom of the physics community that dark matter, a mysterious matter that constitutes 26% of the universe without being seen, is essential to the existence of, well, the universe. However, Professor Rajendra Gupta of the University of Ottawa, Canada, says dark matter is not essential to the existence of the universe. A paper by him published in the Astrophysical Journal on March 15th is causing considerable debate within the scientific community. His second paper follows an equally debated first paper last year, where he nearly doubled the age of the universe from the widely accepted 13.8 billion years to 26.7 billion years, using, among other arguments, the nearly 100-year-old tired light theory pioneered by the Swiss physicist Fritz Zwicky. In a statement, Professor Gupta has said his latest study's findings confirm that his previous work about the age of the universe being 26.7 billion years, and that it has allowed him to discover that the universe does not require dark matter to exist. He spoke to Mayank Reports to make his case. Professor Rajendra Gupta.
You're again creating waves in the world of physics and astrophysics.
Actually, it is the same model which we discussed last
I know.
time, but now it is giving some additional information which is really might provide even more fundamental change to the physics of the universe. Yeah. Last 2 days, I was attending remotely the Royal Society meeting
Right.
in London. It was attended by FRS and Nobel laureates and all those kind of things. I was allowed to attend it, but then they informed me about the availability of seat too late, so I couldn't really go. So I attended by Zoom, and I had some questions which were answered by people who is a Nobel laureate, which was very good. So this was the meeting was concerning the challenges to the lambda CDM model because it is not entirely fitting the new observations. So even people at high pedestals are thinking there may be a problem with this model.
Oh, that's wonderful to know. To come to the main focus of our conversation, your latest paper published last month in the Astrophysical Journal
Yeah.
essentially makes the case that there is no need for dark matter for the universe to exist. That flies in the face of decades of scientific wisdom. Make your case for my lay viewers, if you don't mind.
They actually we have to go back and see why they needed the dark matter. Dark matter was originally thought to account for the abnormal galaxy rotation curves. These galaxy rotation curves could not be explained with the stellar mass they could calculate for a galaxy. And this is why there must be something hidden there which we can't see. So there could be matter like planets don't radiate light. So there may be a lot of such things which might be hidden there, and they might be causing this kind of effect that the orbits of stars in the galaxy, they were moving faster than expected from the visible mass, baryonic matter, what we call. So this is why in the early 20th century, there was predictions made that maybe there is a dark matter. But then they were not considered very seriously. They said, yeah, there could be, but what could be the cause? But then what happens? There were models, cosmological models. This is I call astrophysical observations, which gave rise to this kind of dark matter thing. And since they could not find any other reason, they just said there could be some hidden matter there. Okay. Now, when people got into cosmology, then this was not considered that the dark matter or any kind of just the regular matter. But when the Hubble Space Telescope was reached, and there a lot of new information started coming in, then the cosmological models, which simpler models which existed at that time, they could not really explain the observations. So they brought back something called into the equations the cosmological constant, which Einstein despised, although he introduced, but later on he wanted to remove it. But they brought it back, but even with that one, they were not satisfied. The observations were not satisfied. So equations, when they wrote, they could only be satisfied with a relatively large amount of matter, which could not be again explained through the observational matter which is in the universe. So they said, okay, this is must be dark matter, and this dark matter must be the same dark matter which causing the galaxy rotation curves.
In a statement after you published your paper, you said that your study's findings confirm that your previous work about the age of the universe being 26.7 billion years, and that it has allowed you to discover that the universe does not really need dark matter to exist. How do you prove something this profound? Do you think there are possibilities of experimentally eventually proving what you're saying?
Indeed, see, cosmological observations are the one which are we have to see how much our model can explain. Initially, when we say age of the universe thing back in last summer, then the age of the universe was mainly based on the galaxy sizes which were observed by James Webb Space Telescope and then confirmed by supernovae observation in the near universe, you might say. So that was that showed that the model has some teeth, you might say. It has some credence, you might say. Now, but that's not good enough. You have to see whether it can satisfy other cosmological observations. So we said, all right, at that time we published because it was very exciting and a lot of things were going on about James Webb Telescope, this so-called impossible early galaxy problem. So it was very topical, you might say, at that time.
Right.
But that was not good enough. Or people were criticizing, as you know, the model we had proposed. So we said, okay, no, not only because of criticism, because that is normal nature of research. Okay, you have proved something in a limited domain. You want to increase the size of the domain and say if it is still applicable. So we say, okay, we are going to do something simple. Many complicated things can be done, but what can be done with limited resources which we have? We don't have the kind of resources which Lambda CDM has, thousands of people or hundreds of thousands of people working on that and billions of dollars of investment going in that in different forms. So we don't have that kind of thing. So what we can do, we can take some simpler things. That is what we did in the second paper. We said, okay, cosmic microwave background, simple part of that is the sound horizon. The total CMB, cosmic microwave background, anisotropy or power spectrum will take more time and resources to do it, which I'm working now with somebody, and hopefully we will be able to publish in the near future those findings too. But we took the simpler part of that, which is called the sound horizon, because it is measured by Planck satellite in the sky as angular size. So we know what the angular size is. Now that angular size, if it is depending on what a model gives this distance, could correspond to a small physical size or very large physical size. is the angular size which we measure. So we say, okay, we take that angular size, and we were able to match that with our model, but that's not good enough. Those features also develop this perturbation or features in the early universe. These things develop into what you might call eventually into large galaxies. So we have to see whether this model fits the distribution of large galaxies. So this is given by some kind of 2-point correlation function. And that's another thing we did with that, and this is the reason we published in that one. When we were able to confirm that it fits these two extreme, very early universe and late universe data, then it gives us some confidence that even more difficult data might be possible to fit in. And then we further analyze this, whether what are the contents of the universe. Even in the earlier part, first paper which I published, we could have derived this thing which we have presented in second paper, but then we don't. Our emphasis was more on the other side of it, fitting the early galaxies sizes rather than the existence or non-existence of dark matter or dark energy.
For your theory to hold water, do you think, Professor, that the universe's age is relevant here? What if the age you retain the way it has been, and do you think your theory will still work, or it has to be 26.7 billion years?
Actually, this is, you cannot just arbitrarily set the age. You can't say, okay, let me reduce the age. You can't, because this is what the model is giving. Then we can use another model like the original lambda CDM model combined with the tired light, which was also in the first paper we had analyzed. It was giving somewhat smaller age, about in the range of about 19 gigayears. Bringing in the tired light really reduces the rate of expansion, how fast the universe is expanding. But it reduces that more in the model I have proposed based on covariant coupling constant and in the lambda CDM model. Now, I cannot arbitrarily say, now let me reduce the age of the universe. Now, yes, but your question is very valid. If the age of the universe is less, then people will say, okay, without dark matter, how I am going to form the galaxies? Because galaxies formation will be delayed because dark matter potential, which really draws the matter in the formation of galaxies, is not there. But now, another paper which is now under review by Astrophysical Journal, say same journal where my second paper was published, that paper clearly shows that the galaxy formation is possible. In fact, not only possible, it is possible at an earlier time in the universe than possible with the lambda CDM model because of the age of the universe.
I see. In order to back up your theory, as you point out, you went back to Fritz Zwicky's tired light theory and then combined it with your new covariant coupling constant. Would you care to talk a bit about that constant, the covariant coupling constant? I'm trying to wrap my head around that a bit.
Actually, covariant coupling constant is what Dirac had proposed, that gravitational constant decreases, its strength of the gravitational constant or coupling constant decreases with time based on the expansion of the universe in something called large number hypothesis he had analyzed. So I said, okay, that's fine if that happens. But when that was few years ago when I was working on that. But later on I find, why only gravitational constant? There were a lot of criticism about that gravitational constant cannot vary. There are a lot of studies done and measurements done at cosmological scale and laboratory scale, and they found it does not vary. All right. Why it doesn't vary? That is the question came to the mind. That is where this idea of covariant coupling constant came.
I see.
When I was studying this, I was found there are multiple constants involved, and if they evolved in certain ways together rather than independently, then they cancel each other, and you will not be able to measure their variation. So there is a single function which determines the variation of all these constants. This is what came out, and that was the basis of my this covariant coupling constant.
I see. A feature that I did not elaborate on during our last conversation was the fact that you point out that in standard cosmology, dark energy causes that accelerated expansion of the universe, but in your version, it is due to the weakening forces of nature as it expands, not dark energy. How did you hit upon that particular perspective?
Actually, it comes out of by solving the equations.
I see.
What turns out, this function, this dimensionless function, which relates the variation of various constant,
Mhm.
this function itself shows that all these constants are decreasing in strength, not only gravitational constant, but all the constant like Planck constant, Boltzmann constant, speed of light, they all are decreasing with time. And as a result, we have this kind of effect. Why? There are two ways you can say universe is expanding. Something is pushing the or something is acting against the gravitational attraction and pushing the galaxies away. And that's why universe is expanding. Second thing could be that the forces of nature are weakening. That will also lead to the same effect. Because if attraction, which is binding or bringing the things together, that was the original, before this accelerated expansion was found, people were thinking eventually the, this is decelerating. The universe expansion is decelerating, not accelerating.
Right.
Acceleration is the one which gave somebody a Nobel Prize,
Yeah.
Professor Rees. He got Nobel Prize because of that. But really, what is causing that expansion was then that's when they have to bring back the dark energy, which was or cosmological constant, in fact, and then it was related to the dark energy.
I see. This is perhaps not directly connected with our conversation, but I'm curious where you think Roger Penrose's conformal cyclic cosmology model might fit in your scheme of things.
Actually, I shouldn't comment on that because I don't understand that uh, well enough to be able to comment on it, I should say.
I see, because his point has been that it's eon after eon after eon. In fact, he's on record to say, and this is his specific quote, that it's a bit like Hindu philosophy. These are his words, not mine. So if that is the, let's say for the sake of argument, intellectual argument, if that is the case that the universe has essentially always existed, then all of this worry about its age, its acceleration, all of that goes away, doesn't it?
Actually, one of the things we can say that even if the universe always existed,
Mhm.
it does not mean it couldn't have gone through a collapse and expansion phases.
Right.
It could have perpetually gone in this. But the problem is with the knowledge we have from observation and experiment in the sky, we can only extrapolate it to that extent, which we can say age of the universe. Beyond that, we don't know what happened. This is why we have a lot of theories. Okay, universe collapsed at that point, and it started really um, expanding again. There are a lot of theories like that.
Right.
But those are speculation, they are conjectures, they are all these things you can think of, but there's no proof for that, because
Right.
we can only scientifically, we can philosophically, you can say whatever you want, but scientifically we can only say we can go only that far in the past.
Right. I'm curious about whether what kind of pushback you felt after your two papers, because my limited sense talking to other physicists is that they are not particularly convinced by this, and there may be sort of an establishment pushback to your claim. Do you feel that as a scientist?
Actually, this is natural. I don't think there's any big problem with that. This is the way science should develop. Otherwise, every day people are making proposals. The new things are coming. But they have to be thoroughly established based on scientific verification at multiple stages. Until that happens, they should be skeptical. There's nothing wrong being skeptical. That's the way science improves. And that's the way I am interested in trying to see where my theory might fail. Is okay.
It's
This is
perhaps
a very important part because I'm a scientist. I do the same when I review people's paper. I'm skeptical when they are putting new ideas, and especially if their domain, application domain, is so limited. I'm going to say, okay, what beyond this domain? Does it apply beyond that domain?
right. It's perhaps a wrong question to ask of you, given what you've already told me, but I'm going to ask it anyway. Are you wedded to the age of the universe that you have established, 26.7 billion? Or you think it could change with some other calculations?
See, nobody is wedded to anything in
Okay,
science. Science is by proof.
right,
Tomorrow, you know, at the time when Hubble made the observation, the age of the universe was only 2 billion years. When Dirac made his prediction about the variation of the gravitational constant, it was 2 billion years. Then it kept increasing, and at one point, people were saying it could be 12 billion years or 20 billion years. We don't know really. So it was very much uncertain. Its lambda CDM model, when it came after the Hubble telescope, space telescope launch, that's when we try to start seeing these ages to be crystallized to this number which we have, 13.8 billion years at present. But really, this is a lot of observations in the past on the stars were showing the age of the stars are more than the age of the universe. But then these stellar models have so many parameters which then people rapidly adjusted to fit within the model. Now, Methuselah, even that star, which people talk up to now, they were talking, oh, it has age more than 13.8 giga years or billion years. Now, some people have worked out details and said, no. We have found a way of making sure it is not more than 13.8 billion years. Of course, once you know your limitation, you try to fit within that. Yeah, if you don't fit that, you are outcasted.
right.
So this is the problem.
I'm trying to understand again, Professor, it's a broader question. How important is it for us to know or establish the age of the universe in order to understand the forces within which animate it? It is how relevant the age is eventually, whether it's 1 billion or 30 billion. We are trying to understand what animates it, how it works, right?
Actually, the reason age is important is that how do you form the structures of the universe? How the universe evolved? So many observables which are in the sky, how can they be explained within certain age? And that's where the importance of age comes in.
I see. Given your Indian background, I'm going to ask you this one more time. how frequently do you lapse into philosophical view of what of the work that you do? Because I'm sure you must wonder at the size and the complexity of the universe and the purpose and the meaning, which I personally don't think there is any. How do you look at it?
Actually, that's a very good question. How do you look into it? We are again looking into very narrow field, you might say. The things around us, how even a small living being is created, tiniest amoeba is created. We don't even we don't even know that at present.
Right.
So what we are trying to do, we are atoms, for example, how the atoms or nuclei in particles and various elementary particles, how they are came into existence. So our nature is to really go and try to study whatever is around us. In cosmology, astrophysics is one of that field. So there's so many things to wonder philosophically which are around us, and all you can do is specialize in one thing. And if you are, and everything else, you do wonder like an amateur why it is there. Everybody does.
No, fair enough. But I'm saying someone with a keen mind like yours at some point must wonder about what you're looking at because it's baffling, mystifying all the time. It's almost as if the universe is messing around with us in some ways. That you take one step, I'll take three steps. That seems to be the sense one gets as an outsider to this world.
Yes, and that's the advantage of being outside of the world. But the problem is when you are inside some field, you still feel the same. That you take one little, you think you have taken a large step forward by launching the James Webb Space Telescope. Now you can see even deeper. And now you find we know even less than we knew before.
Right.
So this is the problem. This is the this is the you might say paradox. More you know, less you feel you know.
That's right. But perhaps it's an eternal search at a philosophical level. That it's not. It's maybe it's not a conundrum or a problem waiting to be solved. It's just there, and you just keep taking little pieces out and studying it.
Yeah, exactly. That's all what we can do. We can just tackle the small problems we have with us without worrying about the global problem, unless you are Modi or Biden or somebody. Otherwise, you just keep working in our limited space.
Okay. On that note, Professor Gupta, it's always a pleasure.
Can
I
I say something more? Because
no,
I was
I would be very happy. Please do. Please do.
one the thing I wanted to say that about the dark matter
Right.
situation. That's where we started our talk. This is something not very different from the so-called luminiferous ether theory, which existed for 200 years from the time of Newton and until the experiments done by Michelson Morley and the theory of Einstein. Everybody at that time believed in ether theory. All the big minds, including Maxwell, including anything Newton. Newton, although he was proponent of the corpuscular theory of light, he still, to explain certain observation, he has to call on the ether theory. In waves, if the wave theory which came into existence, wave theory could not be explained according to those people of those times without having some medium through which waves can propagate. So they had to call on this kind of thing, including Maxwell, as I said, who wrote the fundamentals of electromagnetic fields. So everybody believed for 200 years. So the kind of thing, why? Because that's what was able to explain what they were observing at that time.
Right.
Today, the same thing happens. Today, dark matter and dark energy is able to explain something they are observing uh, around them. There are other options which are, even in the days of ether theory, people did propose something, but they didn't get anywhere. So similarly, people are proposing a lot of things today. And and what we have to see how long this dark matter, which nobody has ever observed, they have predicted so many different type of particles that they might explain the dark matter. Billions of dollars have been spent on that in space and on ground, but nothing has been observed.
Right.
And this is what I might say, that my theory might be wrong. I don't say it is. It might be one of the theory which goes on the wayside in
Right.
future. But at the same time, there is people who do work with dark matter and all that. They are themselves not 100% sure about it, that it is there. All they can say, they can explain the observations using the dark matter better than anything else.
Right, right. And finally, before I let you go, in terms of having conversations with colleagues of yours who may not agree with your theory, what kind of back and forth do you do with them? What are their main questions about your papers?
Actually, their concern is that does it fit other cosmological data, like the cosmic microwave background anisotropy, which has been
Okay,
observed, the power spectrum, the shape of it, and all that. Does it really fit? Does it fit the Big Bang nucleosynthesis
right,
abundance of elements? You know, so
right.
so many things which are a little bit more complex to do than what I have done up to now. That is their concern. A second concern is that how astrophysical observation. See, this is cosmological thing I'm talking. Cosmological part is one thing, and the astrophysical part, like the rotation of galaxy curve, the rotational curves of galaxies, there are other observations over gravitational lensing and all that. They appear to be more easily explained by invoking dark matter in certain structures.
I see.
How those astrophysical things can be explained. And I tell them that a lot of theories have been proposed, and several theories have been proposed with the alternative, but these are not considered seriously because in cosmologically those theories cannot explain that there is no dark matter. Now
I
my
see.
theory is explaining cosmological sense there is no need for dark matter, so it provides strength to alternate theories which are explaining the astrophysical existence of dark matter.
This is always fascinating. I mean, I may not understand all the intricacies that you describe, but I have a fair sense of where your mind is. This is quite remarkable. My congratulations again on your second paper, and hopefully you'll come up with a third which will prove everything else.
Thank you, Mayank, for giving me an opportunity to talk to you again.